NEC section 455.6 ATWO provides guidelines for sizing conductors used with phase converters that supply specific, fixed loads. This section applies when the conductor ampacity is less than 125% of the phase converter's nameplate single-phase input full load amperes. To understand this better, let's break down the process step by step. Firstly, calculate the motor's full load current. The formula for this is motor horsepower divided by motor efficiency times motor voltage times power factor. In this case, consider a 25 horsepower motor operating at 230 volts with an assumed efficiency of 85% and a power factor of 0.85. The calculation would be 25 horsepower divided by 0.85 times 230 volts times 0.85, which results in approximately 137.3 amps. Secondly, check if the conductor ampacity is less than 125% of the phase converter's input current. The NEC mandates that the conductor ampacity must be less than 125% of the phase converter's full load single-phase input current. This value is typically found on the phase converter's nameplate. For instance, if the phase converter's nameplate indicates a single-phase input full load current of 100 amps, then the conductor ampacity must be less than 125% of 100 amps, which equals 125 amps. Thirdly, size the conductors for 250% of the motor's full load current. According to NEC 455.6 ATWO, the conductor ampacity must not be less than 250% of the sum of the three-phase current rating of the motor. Using the previously calculated full load current of 137.3 amps, we multiply this value by 250%, resulting in 343.25 amps. In conclusion, based on these calculations and the stipulations of NEC 455.6 ATWO, the conductors for the phase converter in this scenario should have an ampacity of 343.25 amps. This exceeds the example phase converter's nameplate single-phase input full load current of 100 amps, thereby meeting the requirement that the conductor ampacity be less than 125% of the phase converter's input current. Let's delve a bit deeper into each step to provide a more comprehensive understanding. To reiterate, step 1 involves calculating the motor's full load current. The formula, as mentioned earlier, is motor horsepower divided by motor efficiency times motor voltage times power factor. It's crucial to use consistent units. Convert horsepower to watts if necessary, remembering that 1 horsepower equals approximately 746 watts. The motor efficiency and power factor are typically provided on the motor's nameplate. If not, reasonable assumptions can be made based on the motor's type and application. Common efficiency values range from 80% to 95%, while power factors typically fall between 0.7 and 0.9. Step 2 requires a comparison between the conductor ampacity and 125% of the phase converter's full load single-phase input current. The phase converter's nameplate is the definitive source for this input current value. If the conductor ampacity is indeed less than 125% of this input current, you must proceed to step 3. However, if the conductor ampacity equals or exceeds 125% of the input current, a different set of NEC guidelines may apply, so it's important to consult the appropriate sections of the code. Step 3 focuses on sizing the conductors to handle 250% of the motor's full load current. This seemingly high percentage is intended to account for the unique demands and potential imbalances introduced by the phase conversion process. It provides a safety margin to ensure the conductors can handle the load without overheating or causing voltage drops. Remember that the calculated ampacity is a minimum requirement. You may choose to use conductors with a higher ampacity for enhanced safety and future expansion. Furthermore, consider the conductor's insulation type and ambient temperature when selecting the appropriate wire size. The NEC provides tables, such as Table 310.15b16, that list the ampacities of various conductor types at different temperatures. If the ambient temperature exceeds 30 degrees Celsius, you must apply correction factors to reduce the conductor's ampacity. Also, if multiple conductors are bundled together, derating factors may be necessary to account for the increased heat generated. It's worth noting that NEC 455.6 ATWO is specific to fixed loads. If the phase converter supplies multiple motors or other loads that cycle on and off, a different calculation method may be required. In such cases, you should consult NEC 430, which covers motor circuits and overload protection. When dealing with phase converters, it's also essential to ensure proper overcurrent protection. The overcurrent protection devices, such as circuit breakers or fuses, should be sized appropriately to protect the conductors and equipment from overloads and short circuits. The NEC provides guidelines for sizing these devices based on the conductor ampacity and the type of load being served. Furthermore, ensure that the phase converter itself is properly grounded and bonded. Grounding provides a low impedance path for fault currents, which helps to protect personnel and equipment from electrical shock. Bonding connects non-current carrying metal parts to the grounding system, further reducing the risk of electric shock. Phase converters are complex devices, and their installation and wiring should be performed by qualified electricians who are familiar with the NEC and local codes. Improper installation can lead to safety hazards and equipment damage. Finally, always consult the latest edition of the NEC and local codes for the most up-to-date requirements. Electrical codes are subject to change, and it's essential to stay informed of the latest regulations. In addition to the aforementioned steps, consider the voltage drop in the conductors. Excessive voltage drop can cause motors to overheat and operate inefficiently. The NEC recommends limiting the voltage drop to 3% for power, heating, and lighting circuits. To calculate the voltage drop, you'll need to know the conductor's length, the load current, and the conductor's resistance. Use appropriate formulas or online calculators to determine the voltage drop and ensure that it falls within acceptable limits. If the voltage drop is too high, you may need to increase the conductor size to reduce the resistance. Another important consideration is the type of conductor material. Copper and aluminum are the most common conductor materials used in electrical wiring. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. However, aluminum is lighter and less expensive than copper. When using aluminum conductors, you'll need to increase the wire size to achieve the same ampacity as a copper conductor. The NEC provides tables that list the ampacities of both copper and aluminum conductors. Furthermore, ensure that the conductor terminations are properly made. Loose or corroded connections can cause overheating and voltage drops. Use appropriate connectors and tools to ensure that the connections are tight and secure. Apply an antioxidant compound to aluminum connections to prevent corrosion. Regularly inspect and maintain electrical connections to ensure their integrity. In summary, sizing conductors for phase converters requires careful consideration of several factors, including the motor's full load current, the phase converter's input current, the conductor's ampacity, the ambient temperature, the number of conductors in a bundle, the voltage drop, and the type of conductor material. By following the guidelines in NEC 455.6 ATWO and consulting with qualified electricians, you can ensure that your phase converter installation is safe, reliable, and compliant with electrical codes. Consider the implications of harmonic currents generated by the phase converter. Phase converters, particularly rotary phase converters, can produce harmonic currents that can negatively impact the power quality of the electrical system. Harmonic currents can cause overheating of transformers and conductors, as well as interference with sensitive electronic equipment. To mitigate the effects of harmonic currents, consider using harmonic filters or reactors. These devices can reduce the amplitude of the harmonic currents and improve the power quality. Consult with a power quality expert to determine the appropriate type and size of harmonic filter for your application. Also, consider the location of the phase converter. Phase converters can generate noise and vibration, so it's important to locate them in an area where these effects will not be disruptive. Avoid installing phase converters in close proximity to sensitive equipment or occupied spaces. If noise and vibration are a concern, consider using vibration isolation pads or enclosures to dampen the noise and vibration. Additionally, ensure that the phase converter is properly ventilated to prevent overheating. Phase converters generate heat during operation, and inadequate ventilation can cause the unit to overheat and fail. Provide adequate airflow around the phase converter to dissipate the heat. Consider using fans or louvers to improve ventilation. Finally, keep in mind that phase converters are specialized devices that require specific maintenance procedures. Follow the manufacturer's recommendations for maintenance and service. Regularly inspect the phase converter for signs of wear and tear, and replace any worn or damaged parts. Keep the phase converter clean and free of dust and debris. By following these maintenance procedures, you can extend the life of the phase converter and ensure its reliable operation. Let's also address some common misconceptions about phase converters. One common misconception is that phase converters can be used to power any three-phase load. While phase converters can indeed power a wide range of three-phase loads, they are not suitable for all applications. Some loads, such as variable frequency drives, may require a true three-phase power source. Consult with the equipment manufacturer to determine the compatibility of the phase converter with the intended load. Another misconception is that phase converters are always the most cost-effective solution for powering three-phase equipment from a single-phase source. In some cases, it may be more cost-effective to install a new three-phase service from the utility company. The cost of installing a new three-phase service will depend on several factors, including the distance to the nearest three-phase line and the capacity of the existing electrical infrastructure. Obtain quotes from the utility company and compare them with the cost of purchasing and installing a phase converter. Yet another misconception is that phase converters are maintenance-free devices. As mentioned earlier, phase converters require regular maintenance to ensure their reliable operation. Neglecting maintenance can lead to premature failure and costly repairs. Follow the manufacturer's recommendations for maintenance and service to keep the phase converter in good working condition. In conclusion, sizing conductors for phase converters is a critical aspect of electrical installation that requires a thorough understanding of NEC guidelines and best practices. By following the steps outlined in this discussion and consulting with qualified electricians, you can ensure that your phase converter installation is safe, reliable, and compliant with electrical codes. Remember to consider all relevant factors, including the motor's full load current, the phase converter's input current, the conductor's ampacity, the ambient temperature, the number of conductors in a bundle, the voltage drop, the type of conductor material, harmonic currents, location, and maintenance. With careful planning and execution, you can successfully integrate phase converters into your electrical system and power your three-phase equipment efficiently and safely. Finally, always prioritize safety when working with electricity. Turn off the power before making any electrical connections, and use appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working with electricity, consult with a qualified electrician.